Okay, in this video I want to talk about the definition of the definite integral. And the thing I have boxed up here in red at the top is the definition of the definite integral. And it says that the integral from a to b of f of x dx is equal to the limit as n goes to infinity, the summation from 1 to n, f of x sub I star delta x. And you may have seen that this value on the, either side, this integral from a to b of f of x, what that represents is you're finding if the function's above the x-axis, you can think about it as being an area. So what we're doing is we're calculating the area between the function f of x and the x-axis between the x-coordinates of a and b. That's what this represents. Again, you can only really think of it as being an area if the function's above the x-axis. So let's just try to talk about why these two definitions, where this definition basically on the right-hand side comes from. So again, here's my little function, or my graph f of x between a and b. What we're first going to do is, instead of actually calculating the area directly, we're going to approximate the area. Okay? And this is the whole basic idea with integration in general. You end up somehow doing an approximation that's somehow easy to do, and you use that approximation to eventually come up with the actual value. Okay, so a couple things we're going to do. What we do is we chop up our interval from a to b into n pieces of equal width. Okay, so I'm going to chop it up into a bunch of pieces. Each piece is going to have width, we label that delta x. Okay, so that's the value of the width of each little segment. And notice delta x is going to have value. Well, what's the length of the interval? The length of the interval would be b minus a. And since we're chopping that interval up into n pieces, the width of each piece would be b minus a divided by n. Okay, so that's going to be the width of each little piece. The way that we actually go about approximating the area is, okay, so the basic idea, let me again label some stuff here. Here's some generic x-coordinate, and there's the one after it. Let's look at this interval. I'm going to call this the interval x sub I, or this little point x sub I. The one previous to it, that'll be x sub I minus 1. Okay, so again, just trying to label things generically here. If we take any point inside of there, that particular interval, we'll label that point as x sub I star. So again, the star just kind of represents, hey, this point is in this ith interval. Okay, whatever interval it is, the first, second, third, fourth, the ith interval. What we do is, for every interval, so maybe I'll pick on this interval, we make a rectangle. The way we go about making a rectangle, again, is we take any point in that interval and we extend it up until it hits our graph. And then we extend that little height over until it extends over the interval. Okay, so now I've got a little rectangle here. Well, the area of this ith rectangle, so let me call that a sub I. The area of the, or even let me call this the area of the, we'll label it as r sub I. For the ith rectangle, what is the area of that ith rectangle, this green rectangle? Well, the width of it, we just said is delta x, whatever that value is. How do you get the height of that rectangle? Well, you would plug your function, your x-coordinate x sub I star into the function. Whatever that y-coordinate is, that would be the height of your rectangle. So the height of the rectangle would be f of x sub I star. Okay, so that's the area. This represents the area of this ith rectangle. Well, what we do is we basically cover up our region. For every interval, we take a point, okay, and we get a rectangle. Again, we could calculate the rectangle, the area of this rectangle, by calculating its width and its height, the exact same way we did here. And again, we just do this for every single interval. And it's easy to figure out areas of rectangles. Okay, so the idea is we put rectangles over this entire region. So we could now approximate the area underneath the curve. I mean, the area is going to be roughly equal to the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle all the way down the line. Well, if we chop our interval up into n pieces, we are going to have n rectangles. Okay, so what do we have to do? Well, the area of the first rectangle, again, I'm going to take a point x of 1 star, so that comes from the first interval. I'll multiply that by delta x to get the height and the width, so that'll give me the area of the first rectangle. Plus, I'll get f of x of 2 star times delta x. That's going to give me the area of the second rectangle, and I'll do this all the way down the line until I get to my last rectangle, which is f of x of n star times delta x. Okay, so again, we have to remember what we have right now is still an approximation. So let me give myself a little more space here. So again, the area is roughly equal to this bottom thing. We can rewrite this area using summation notation as the follows. Well, we can write this as the sum from I equals 1 to n of f of x sub I star times delta x. Okay, so that's a more compact way for writing the sum at the bottom. Again, though, this is just an approximation to the area, right? If I use n rectangles. The basic idea is to get a better approximation, you should use more and more rectangles. So imagine, just cutting this interval up into 2 pieces. You're going to get 2 big boxes. The area of those 2 big boxes is probably not going to be close to the correct area underneath the curve. The more boxes, the more rectangles you use, the better that the approximation becomes. Well, the way mathematically we say use more rectangles is we let the limit as n goes to infinity of this summation from I equals 1 to n of f of x sub I star times delta x. Because what are we doing? Again, the approximation was just when we used n rectangles, so now we're saying let the number of rectangles go off to infinity. And the approximation gets better and better and better. By calculating that limit, we can say that the true area underneath the curve would therefore be the limit of those approximations. Okay, and that's the basic idea. That's the reason why when you go to calculate an area underneath the curve, you're using this definition. Okay, the problem is, how do you actually calculate something like this? Well, the point is, if you've seen the rules on finding antiderivatives, all you have to do is find an antiderivative for your original function, plug the upper limit of integration in, the lower limit of integration in, subtract the two, and that'll be your solution. So obviously the key to calculating this is being able to find antiderivatives, and that's a lot of what you do in calculus too, because that's kind of, if you can't find the antiderivatives, you're stuck. So hope this helps. Definitely in other videos I have some actual concrete examples of finding antiderivatives. So again, this is just the basic idea in understanding this definition of the definite integral.